So continuing our investigation of logarithms, there are 6 properties of logarithms. There's more than 6, but these are the 6 I feel that are going to be most important that we're going to be utilizing throughout the course. What you might want to do is go ahead, after you guys take a look at these, pause the video and copy them somewhere in your notes, so that way you have them somewhere very accessible, or even make like a flashcard with all of these on here. Okay? These are going to be very critical to helping you guys solve equations, and then later in the course being able to work with logarithms and simplifying. So I have these 6 properties. Hopefully you copied them somewhere. One of the things we want to do is, if I give you a number of logarithmic statements, for you to be able to simplify into a single logarithm. So let's take a look at several of those types of examples. So I want to write as a single log. So let's say for letter A, we'll do something fairly basic. Let's say I have something like log 2 of x squared plus log 2 of x to the 5th minus log 2 of x to the 6th. Okay. And what I want to do is I want to simplify that into a single logarithm. Okay. What we can do first is we can take a look at rules number 1 and 2. Rule number 1 says that if I add 2 logs, I multiply whatever those operands are. And then if I subtract 2 logs, I divide whatever the operands are. So what I'm going to do is I'm going to rewrite this into a single log as log 2, since the coefficient of x squared is positive, goes on top, plus log 5, or log base 2 of x to the 5th, so x to the 5th goes on top, and then since we're subtracting x to the 6th, the x to the 6th is going to go in the denominator. Okay? So hopefully you understand that all you're doing is you're just, anything with a positive coefficient is going to go in the numerator, anything with a negative coefficient goes in the denominator. Of course, we can still simplify this. If you remember your exponent rules, if you have 2 of the same base, you add the exponents. So this becomes log base 2 of x to the 7th over x to the 6th, just by adding. And then you also probably remember that if you have 2 of the same base, you subtract the exponents when dividing. 7 minus 6 just turns into x to the 1st, so this ends up being log base 2 of just x to the 1st power. And the neat thing about that is, didn't we graph log 2? And we know its domain, we know its range, we know the vertical asymptote for it, we know what it looks like. It's much easier to deal with this statement than this ugly statement right here. Okay? So certainly, it's one of the benefits of being able to simplify is to work with obviously more recognizable sorts of logarithms. Let's take a look at another example. Perhaps something like this. Let's say I have something to the effect of 1/3 quantity 2 log base 7 of x minus 3 log base 7 of y plus 7 log base 7s of z. All right. One of the things that you're probably thinking is right away, well, let's just distribute the 1/3. That's certainly fine. Another way you could do it is to operate inside, but I think it's best to just go ahead and distribute, then we can work from there. Okay, so by distribution of our 1/3, we get 2/3 log 7 of x minus 3 times 1/3 is just 1, so I have a log 7 of y. And then since the 1/3 is not connected to the 7 in any way as the coefficient of log 7z, I just still have plus 7 log 7 of z. course we want to try to write this as a single log. But unfortunately, unlike the previous example, we see that there's some coefficients. So let's take a look back, and don't we have this rule number 3 that says if you have a coefficient r, you can make it the exponent. So let's just go ahead and make 2/3 the exponent. Let's just make 7 the exponent. Okay? So we're going to get log 7x to the 2/3 minus log 7y plus log 7z7. Now it looks a lot like the previous problem. Let's go ahead, let's meld it into one super logarithm. Okay? Remember the rule, if it's a positive coefficient, it goes on top. If it's a negative coefficient, it ends up in the denominator. So, one possible answer that you could see is that this is going to be log 7 x to the 2/3 because we have a positive coefficient, z to the 7 because that has a positive coefficient, and then finally because it has a negative coefficient, the y is going to go in the denominator. Certainly one way that you could write the answer. Some of you may remember that it is possible to take a fractional exponent and write it without the fractional exponent. Okay? What you may remember is that you can write it as a root. Okay? The 3 is the index, and the 2 is going to stay as the exponent. So this is more of like the traditional way that something like this would be written. Instead of having x to the 2/3, it's still going to be log 7. And again, every time from now on we see fractional exponents, we need to make sure that we can convert them back into rational and radical expressions. So this is going to be the 3rd root of x squared. Okay? So, this guy that I underlined in green is the same as this guy that I underlined in green. That's just an algebraic step. Okay? Hopefully you remember that, but if not, now's a chance for you guys to go ahead and practice that to make sure you're good with it. And then finally, we still have z7 over y. So this would probably be, I don't want to say the more correct, but the more traditional way that something like that's written. Okay. Make sure you can simplify by writing it as a single logarithm. Okay, we're going to see that that's going to be important when we go to solve equations. All right. What if we just want to get a numerical answer? There are some problems to where I'm going to ask you to be able to simplify it and get an exact value. Let's see if we can do those types. And again, we're going to hold on to these rules. So let's see if we can find an exact value without a calculator. As you guys are finding out, I really like to not use the calculator, especially for those of you guys that are going to go to Calc 2 and Calc 3, where you start using multivariable expressions. So you might not even have numbers. You have to know the rules to be able to work with it, and your calculator basically becomes useless at that time. All right, how about something like this? Okay. Let's say I have log base 2 of 1/8 plus 2 natural logs of e minus e to the ln of 7. I'm betting there's 2 of these statements or these terms that you know easily what to do with, because you look at rules number 5 and 6 and you can say, oh, okay, well, e's and ln's are inverses of one another. They cancel each other out. So what you might automatically say is that, oh, okay, well, this guy right here, the e to the ln 7, just looks exactly like rule number 5. So it's just going to simplify into a 7. Okay? And because we have a minus here, this is just going to simplify into the minus 7. So that's easy enough. All right. This guy right here, well, there's a 1 here, isn't there? There's sort of like that implicit 1. And if you look at rule number 6, ln of e to the x is equal to x. In this case, x is 1, so this just becomes 2 times 1. Okay. Or we know that's going to work out to be 2, just illustrating where the 1 comes from. This guy is something that we did at the beginning of this section with logarithms, where you guys were asked to be able to do it by hand. Remember, let's do this off to the side, so we're okay. What we probably want to do is say, okay, log base 2 of 1/8 is equal to x. We don't know what it is, so we're going to set it to a variable. Our mantra, logarithm is an exponent. X is the exponent, 2 is the base. So, if I was to rewrite this using my mantra, 1/8 base 2 x exponent. We saw how to handle fractions, didn't we? We saw that instead of 1/8, we can write that as 8 to the minus 1. We know that 2 raised to the third is going to be 8. And hopefully it's fairly easy to see that you can multiply the 3 and the negative 1 to get 2 to the minus 3 equals 2 to the x. Okay. Or in other words, negative 3 equals x. All right. So essentially, if I was to couple all this into one answer, I have negative 3, which is from here, plus 2 minus 7. Okay, so let's kind of finish this off. We have negative 3 plus 2 minus 7. Okay, that's from our 3 parts, and clearly that's a negative 8. So it is possible for us to be able to evaluate some of these sorts of exponential and logarithmic expressions without using a calculator. Of course you can use the calculator to verify your answer, okay? But unfortunately, if I ask you all to be able to utilize these without the calculator and you rely on the calculator, you're not going to get too far when you take your quiz and your exam. So practice a few of these on your exam, on your homework. It's on assignment number 2, and these are problems like numbers 3 and 5. One other type of thing we need to know before we can move on to trigonometric expressions is we need to know how to find the domain of a logarithm. So let's talk about that. It's a fairly easy sort of thing, because we always need to know what stuff to plug into a logarithm. And we talked a little bit about this when we talked about the graphs of the logarithm. Just to motivate this, so this is domain of a logarithm. Remember the function which we graphed, f at x, log 2 of x. And you guys might recall that this is about what the graph looked like. Of course, if you don't believe me, use your calculator, get your change of base formula to remind yourself, or just look back at the video from the previous section. Right. What we can see is that the domain is from 0 to infinity. So in other words, x has to be bigger than 0. So every time I look for the domain of a logarithm, okay, if I have a function f at x equals log base b of x, what I'm saying is that x better be bigger than 0, otherwise it's not within the domain. Whether b is 2, whether b is a half, whether b is 99,000 pi, it doesn't matter. Okay, so this is provided that x is bigger than 0. Let me show you 2 examples where you can easily find the domain of a function that's logarithmic without having to look at its graph. And that's where we want to get to. So, for example, let's find the domain of the logarithmic function. Okay. Let's start off with an easy guy. Let's say we have f of x equals log base 8 of 3 minus 7x plus 12. And I want you to be able to find the domain of this guy. Okay? All I'm concerned about is what's operand, or the operand of the logarithmic expression. So, get rid of the log 8, get rid of the 12, and all we care about is this stuff right here. In other words, 3 minus 7x has to be bigger than 0. This is true for every logarithm. Obviously, to solve this inequality, we can either add 7x or we can subtract 3 from both sides. I'm going to add 7x just to keep everything positive, nice and easy. So I get 3 bigger than 7x, dividing by 7, 3/7 is bigger than x. Okay? And just like the domain problems that I'm asking you guys to work, I always want you to write it in the interval form. Okay? It might help to graph it. If I graph this guy on the number line, 3/7 is right here, and everything is less than 3/7. So if you're one of those people that doesn't really get interval notation too well, what might be helpful is to graph it first, and then you can kind of see, oh, okay, now the shaded area is from -infinity to 3/7. So the interval -infinity to 3/7 is the domain of this logarithmic function. Pretty easy, right? It's just an algebra equation that we have to solve. And interval notation, although a lot of students don't recognize it initially, is something you guys will pick up fairly quickly. Another example. Let's say I have the natural log, ln, of 2x squared minus 50. I'm sorry, I should probably make that a function first. So let's call it g of x. G of x equals the natural log of the quantity of 2x minus 50 plus 7. And I want to find the domain of this function. Well, just like we did in the previous, ignore all the stuff that's going around there. This guy right here is all we care about. So we care that 2x squared minus 50 is bigger than 0. Now, of course, we have to solve this. There's a number of ways we can solve it. Okay? Let's go ahead and factor out a 2. Or we can even divide by 2. Because we're allowed to divide everything by 2. So we would get x squared minus 25 bigger than 0. Okay? And doesn't it just make sense that this number x had better be bigger than 5, since 5 squared is 25. Okay? Also, shouldn't it be less than -5?